Hi guys, today I'm talking about the Helium Pycnometer. The Helium Pycnometer is an equipment used to determine the skeleton density. In this video we will see briefly how the equipment works and how it converts the collected signals into results, and that we will see the mathematics behind its method. Let's go. Here we have a spreadsheet developed in Excel in the VBA, Visual Basic Application, programming environment for simulating the operation of the equipment. In this first frame, we have some characteristics of the material being analyzed. On side the mass of the material, remembering that the helium pycnometer determines the volume, real or absolute, of a sample. So the mass must be verified. The material must be weighed beforehand, as the mass value is included in the calculation that the equipment performs. This other frame shows the result calculated by the equipment and below the equations used for this calculation. And finally, here below the structure of the equipment. The equipment is composed of two chambers that we will call here Chamber 1 and Chamber 2. Chamber 1 is where a standard sphere will be placed later. That is with the no volume for the calibration of the equipment. The step where the volumes of the chambers 1 and 2, and then where the sample will be placed to determine its volume. There are equipment in which the sphere and sample are placed in chamber 2. Change the calculations a little, but the principle is the same. There is also a pressure gauge. In this example, we will use the measuring of pressures in PSI and a temperature gauge. The signal that matters for the determination of the volume of the sample is the pressure. The equipment usually only has one pressure gauge. Here we have two because I use it for other examples of interferences to the test that I will not discuss here. Some equipment also have a temperature meter. Here I left two as I used them to show the influence of the results when the system is not in thermal equilibrium, but I will not address this subject now. We have a helium gas inlet. This is the gas used in the analysis because it is inert, non-reactive, and of a size that allows it to occupy space in permeable form. Therefore, we call the density obtained by this technique real or absolute, as it only considers the real volume of the sample. This regarding P space between particles and part permeable to helium. We also have a set of three valves. The first for releasing helium gas into chamber 1, a second valve for releasing the excess of helium gas in the second chambers, and a third for expelling the gas. Let's divide the operation of the equipment into three steps. The first, determination of the volume relation between chambers 1 and 2. The second, determination of chambers volume with the idea of a standard sphere. And the third, the determination of the actual volume of the sample to determine the density. Initially, let's fill in some values for the simulation. Sample mass, 100 grams. Density of the sample, 2.21, assuming it is hydrated lime. Test temperature, let's leave it 23 degrees Celsius. Remembering that the test temperature must be the temperature at which we want to express the result, as the temperature influences the volume of the material. Strictly speaking, the most correct thing is to express, in addition to the density value, a temperature and the relative humidity that the material was conditioned, as the material may contain absorbed water. Some standards define this condition and the precondition criteria in order to standardize the test and make it reproducible. And here the volumes of chambers 1 and 2 and the volume of the standard sphere. Now that we have these parameters defined, let's start the test. First step, determine the volume ratio between the chambers. Here we will determine if the chambers have the same volume or how many times one chamber is larger or smaller than the other. But in this step, we will be able to estimate this relationship, but not the actual volume of the chambers. Opening the first valve, the helium gas will fill the volume of chamber 1. The equipment normally fills up to a value close to 18 psi or 19.5 psi. When reaching the value, the valve is closed, then the valve is expected to stabilize and it is registered. We will register here P1. After stabilization, valve 2 is opened. That gas spreads through chamber 1 and 2. The new pressure value obtained after stabilization is recorded as P2. Here, we already have the volume ratio between the chambers. If the volume of P2 is half the volume of P1, it means that the chambers have the same volume using the general gas equation in a simplified way we have. Pressure 1 multiplied by the volume of chamber 1 is equal to pressure 2 multiplied by the volume of chamber 1 plus the volume of chamber 2. Here we have our first equation. P1, V1 is equal to P2 times V1 plus V2. Then all the gas is released out of the equipment. In the second step, we will carry out the calibration, or better, the determination of the chamber's volume. And for that, we will use a sphere with no volume. With the ball inside chamber 1, the chamber is filled with gas. When the pressure is reached, the valve is closed, expected to stabilize, and note pressure 3. Then valve 2 opens and the gas will spread through both chambers, and here we have pressure 4. We now have two equations, or a linear system of two equations with two unknowns. As the number of the equation is equal to the number of unknowns, it is possible to solve. The second equation is pressure 3 times the volume of chamber 1 minus the volume of the sphere, which is equal to the pressure 4 times the volume of chamber 1, the volume of the sphere plus the volume of chamber 2. Solving this system, we obtain equation 1 and 2 from this table. And so we determine the chamber volume is based on the known volume of the sphere. And finally, the determination of the sample volume, which is enough to remove the sphere and place the sample in chamber 1. The operational part is the same. With the sample in chamber 1, valve 1 opens, The gas will fill the chamber, and after stabilization, P5 is registered, valve 2 is opened. The gas will fill both chambers after stabilization, we register P5. Here we have a new equation where all values are null except the sample volume. P5 multiplied by the volume of chamber 1 minus the volume of the sample is equal to P5 multiplied by the volume of chamber 1 minus the volume of the sample plus the volume of chamber 2. Isolating the sample volume, we have the equation that's here in the table. And as the chamber volumes were previously obtained, we can calculate the sample volume as well as its density. Since the mass has also been determined by external ring, the calculated density may differ a little from the value defined from the simulation due to rounding off, since normally the equipment operating with the determination of pressure in three decimal places. I hope that content has helped you. Until later.